Alright, so hi everyone. So let's talk about the Taylor series. So last time we discussed about truncation error, and we had truncation error because we talked about the Maclaurin series, which is still a Taylor series centered around zero. So let's talk about Taylor series expansions and their use, no, in numerical methods. Usually, I would just give you an idea on, well, how can we basically utilize this for our problems. So this is the Taylor series expansion of a given function. So we have f of x sub I plus 1 is equal to f of x sub I plus f prime of x sub I multiplied by x minus x sub I, and so on and so forth. So as you can see here, we start with a function, and then we substitute the function with with x sub I. And then moving on from this, we have the first derivative, and we introduce here x minus xi, and then this will become second derivative, and then respective to that second derivative is 2 factorial, and respective to the 2 factorial and the second derivative, we have this squared. So you can see the pattern here. This will continue on and on and on at n terms, or the n is equal to blank terms. And as you can see here, we utilize here r sub n, and r sub n here basically is just the truncation error. Okay, so we could approximate a given function using an nth order Taylor series. So depending on how many terms you want or how many terms you want your approximation to utilize, you can find approximation using the Taylor series. So being this an infinite series, we cannot usually utilize this full computationally. We could just truncate. Well, let's say you want 10 terms, 100 terms, 1 million terms. Actually, that will be impractical, but you can do that as well. So the approximation improves as h decreases. So what is h decreases? So h is basically just the difference of your x value and your standard, which is x of I. So let's create some definition here. X is basically just the point of interest. Okay, so you want, let's say you want to evaluate f of x, or f of x. What do you call this? Sorry. F of x is let's say f of pi, and your x of I will be the deviation from that x. So x of I will be the center usually of your approximation. Okay, so the Maclaurin series is centered at x of I is equal to 0. So let's move this here downwards. Okay, all right. So as you can see here now, to visualize the approximation of the Taylor series, if we add more terms, the approximation gets better and better. So let's say we have here a function f of x. We can find the Maclaurin series. Actually, this is a Maclaurin series since it is centered around this point. So the approximation will be better around this portion. So this will be some interval at which the approximation will be good. And you need to add more terms if you want to expand that range. As you can see here, if we add more terms, the approximation gets better and better, as seen by the green line or the green curve. And the true curve is your blue line. Okay, so talking about truncation and route of errors, there is a point of diminishing returns. Let's say you have a computer at which your precision is limited to this amount, and you want to truncate your Taylor series at its highest amount. Let's say you want to truncate it at 100 terms to achieve the precise calculation of this function. It will not really happen just like we imagine it ideally, that if we add more terms, it will have less errors. No? If we add infinite amount of terms, we will achieve less errors when using computers. That is not true. So you will reach a point at which if you truncate more than you can, more than your calculator can compute, you will actually introduce more errors. So the direction here is to the left. So if you add no, more terms, your truncation error will be lower, but your total error will be higher at some point at which your calculator cannot compute precisely. Okay, that is basically the trade-off of truncation and round-off errors at some point. You know? So let's say at some point, let's say at 100 terms truncated, it will not be that optimal. It will introduce more errors compared if you utilize 90 terms. Okay? So there are other sources of errors, which are gross errors or blunders. So what does that mean? So when you implement your numerical method solution, sometimes during your coding or your programming, there is something wrong, instead of the computation. And then the model errors could be, we're talking about the structure of the model. If we're talking about creating a representation of our physical quantity, there will be some structural error involved with that. And then data uncertainty, let's say we are measuring this intrinsic parameter of this physical, let's say the temperature of the object cannot be computed exactly, since there will be some noises around, that could conflict with the accuracy or the precision of your measurements. So basically, this is measurement uncertainty. There are some noises in the data. Okay, so an example here, use Taylor series expansion from n is equal to 0 to n is equal to 4 terms to approximate f of x is equal to cosine x at x is equal to pi over 3 on f of x and its derivatives at x of I is equal to pi over 4. Show the epsilons of t for each approximation. Okay, so how do we do this? So we have a given function, and we want to evaluate this function at this value. So we want to find cosine pi over 3. But instead of just substituting this directly, we will utilize Taylor series expansion. So when utilizing Taylor series expansion, we should have a center. So the center here is pi over 4. Okay. And so how do we do this? So if you can remember the Taylor series expansion of, let's say, f of x sub I plus 1, or sometimes we just utilize f of x. Now this is equal to f of x sub I plus f of x sub I, its first derivative multiplied by x minus x sub I, and then plus second derivative of f of x sub I, and then x minus x sub I squared over 2 factorial, and so on. As you can see here, this is just a pattern. So no derivative, first derivative, and then this is just 1, and then actually this is over 1 factorial, and then we have second derivative squared, and then 2 factorial, and so on. So we have already a given of x of I and your x. Okay, so we can just find also the approximation truncated at n is equal to 0 to n is equal to 4. So let's say when we're approximating from n is equal to 0, your f of x will be approximated as f of x of I. So we truncate this at n is equal to, this is basically n is equal to 0, guys. So if we utilize Taylor series, this is when n is equal to 0. Because it's over 0 factorial, this is the 0 derivative, no derivative. So if we substitute our function cosine x with pi over 3, this will be just pi over 3. So cosine pi over 3 Now we can solve this as this is equal to, let's use our calculators. So we have cosine. Okay, so if we have pi over 3, we have to convert this into radian. So shift mode and then 4 for radian. So we have pi over 3 cosine, sorry, should be pi over 3. And then this will be 1/2. So we have 0.5 or 1/2 for our first approximation. So now how do we find the true error or relative true error epsilon sub t or the absolute value of this? So we know that this epsilon or the true relative error, this is equal to the true value minus the approximate value over the true value multiplied by 100. But since this is the absolute value, we have to find the absolute value of this. So the true value, how do we find the true value? No? So this is actually the approximate value only. Okay, so this is the approximate value only. We want to find the true value. So to find the true value, we just utilize our calculators directly. So the true value here, which is f of x, that is equal to cosine. Sorry, it should be pi over 4 here. I'm sorry, guys. This should be pi over 4. Sorry, I'm really sorry. It's centered around pi over 4, so it should be pi over 4. Sorry, my mistake. So this should be 0.707. 0.707 1. And cosine pi over 3 as our true value. So this is our true value, which is 0.5. Sorry, guys. So therefore, the approximate, sorry, the relative true error will be the absolute value of, we have 0.5 minus 0.7071 over 0.5 times 100. Okay, so this will be equal to, we have 0.5 minus 0.7071 over 0.5 multiplied by 100. So this is 41.42. So find absolute value, guys. Don't forget the absolute value. This will be 41.42%. Okay, so this is extremely high as an approximate error. So therefore, as a true error. Okay, so let's move on with the second n. No? So n is equal to 1. So this is your okay. So this is the approximate f of x. No? Okay, let's find the next n. So n is equal to 1. We have f of x. That is equal to f of x sub I. Okay, so this is when n is equal to 1. N is equal to 1. So we have two terms here. So f prime of x of I, then x minus x of I. So we already solved for this one. So ito na lang solve natin. No? This will be the first derivative. So we want to find the derivative of cosine x. No? Okay, so let's just write here what we solved already. 0.7071 and then plus, or sorry, this should be negative. The derivative of cosine is negative sine, so negative sine. Okay, negative sine of x. So this is x sub I. So x sub I natin is pi over 4. So we have here pi over 4. And then we have here pi over 3, which is our x. And pi over 4 as our x. Okay, so let's simplify this one. Then you can simplify this. I will simplify this first, guys, so that I won't have to write this down every time. So sine pi over 3 minus pi over 4, sorry, not sine, no. Pi over 3 minus pi over 4, that is equal to pi over 12. Ayan, no? So simplifying this using your calculator, your second approximation will be sine pi over 4 and then pi over 12. Okay, so the answer should be 0.52. 0.5220, right? We can round this off. So this will be your approximation at n is equal to 1. Now, to find the relative true error in absolute value, we could just write this down again. So we have here we have 0.5, the true value, and then we have just 0.522 over 0.5 multiplied by 100. So this is 4.4%. Okay, so this is your error, or the relative error. Okay, moving on to n is equal to 2. Let's create another slide. So at n is equal to 2, we are introducing more terms. So this will be approximated to f of x sub I plus f prime of x sub I, x minus x sub I, and then the second derivative, and then x minus x sub I squared over 2 factorial. So this one, we actually solved this one already. That is equal to 0.5220. Now we just want to solve for this one. So f of x is approximately equal to 0.5220, and then find the second derivative. So to find the second derivative, we want to find the derivative again of negative sign. So negative sign x, the derivative of that will be negative cosine x. So this will be negative cosine pi over 4. So our center is pi over 4. And then we already saw this one, that this is equal to pi over 12. So we have pi over 12 squared, since this is squared, and then over 2 factorial. So f of x will be equal to, or approximately equal to, we have 0.522 minus, we have cosine pi over 4 over 4, and then we have pi over 12 squared, and then over 2 factorial. Where's that? Factorial. Okay. We square this. Okay. So the third approximation will be 0.4978. 0.4978. Okay. And then find the relative error. This will be equal to, we have 0.5 minus 0.4978. Sorry, 0.5 times 100. Okay, so 0.44%. Right. 0.44. 0.44%. Okay, for n is equal to 3. So as you can see here, we can just skip everything. So if n is equal to 3, f of x is approximately equal to, so the last portion, 0.4978, and then add another term here. So we have here the third derivative. So we want to find the third derivative. So the derivative of negative cosine x will become positive sine x. No? And then substitute this pi over 4 again, and pi over 12 cube all over 3 factorial. So this will be equal to, or approximately equal to, 0.4978 minus, we have sine pi over 4, and then pi over 12 cube. It should be positive, sorry guys. Positive here, and then we have 3 factorial. So the answer should be 0.499. As you can see, it gets closer and closer to the true value. 0.4999, right? Okay. So this will be your approximate value, and your true error or relative to error will be, so let's calculate this again, 0.5 minus 0.4999 or zero point 0.5 multiplied by 100. So this is 0.02%. Okay. And then for n is equal to 4 plus 1, so f of x is approximately equal to 0.499. So the previous one, previous approximation, plus we have, so the next derivative of this will be cosine pi over 4, and then add the exponent here, pi over 12 to the fourth power over 4 factorial. So add another one here. So our final approximation at n is equal to 4, that will be, so cosine pi over 4, and then pi over 12 to the fourth power, and then 4 factorial. Sorry, factorial. Yeah. Okay, so the answer should be 0.5. So as you can see here, this is accurate at 4 significant figures. So this is your approximation, and your approximate error, since this is already 0.5, this will be equal to 0.00 4 significant figures, which is this. Okay, so that will be all today. Hey guys.